Hello, everyone. I'm Olivier Me. I work for Disney, but today I'm here to present something like completely separate. I'm not here to. It's going to be a presentation about the Unison programming language. I want to start by saying that I really love Scala. I'm not here to diss on Scala. As a matter of fact, I'd like to take a moment to thank everybody who's involved in the ecosystem, whether the compiler or the libraries or the tooling. Round of applause, please, for everyone who works. Yeah. Thank you very much. So that being said, has anyone encountered one of these runtime exceptions before? Show of hands. All right. So these are symptoms of binary incompatibility problems. So typically when you have transitive dependencies that are that sort of carry incompatible versions of the same library, this happens. So it's not a problem that's inherent to Scala, but more on the runtime. Typically, like when you write a library, you're going to give human readable names to the methods and the fields and the classes. And these are inherently mutable in the context of the lifespan of a library. Like when you make some changes to a library and release another version, you're going to change the implementation of some methods potentially, and therefore the pointers to these implementations sort of change values. Terms in the JVM ecosystems are packaged together in classes, and then them classes are packaged together in jars, and the sort of set of all public names that you give your terms form the thing that we call the application binary interface. It's an implicit concept, really. But the sort of defines the outline of the library that the runtime is able to interpret in a way. So jars are uploaded to artifact repositories such as Sonatype at some immutable coordinates, but these coordinates are not really part of the sort of language itself. They're part of the build context. So when, as a sort of developer who writes an application, you sort of start, solving problems and stuff, you're going to depend on libraries, and what you're going to do usually is define the list of your direct dependencies that your code directly invokes. Now, the dependency resolver, which is typically Coursier in our Scala ecosystem, is going to be responsible for gathering the transitive dependencies of all your direct dependencies and make decisions as to which version of each library it should select when formulating the class path for your application, right? So it's usually going to select the latest version of each of the libraries. Now, the thing is that when you, as a library developer, when you sort of have to make an incompatible change to one of the methods, for instance, by adding a parameter or something, you're essentially creating a ripple effect that's going to lead to the class being different and then the jar being different, and this jar is going to carry this incompatible method, right? And jars are not something that are fungible. You can't, like open a jar and pick and mix different methods from different jars together. You need to treat the jars as sort of atomic units for your runtime. So if you have two incompatible versions of libraries in your dependency graph, then your class path is essentially contaminated. And that's sort of what leads to exceptions such as no such method errors. So in our ecosystem, in the Scala ecosystem and the Java ecosystem, we have this sort of supply chain issue that basically like we're trusting the pinky promises of library developers around not breaking APIs, right? Because as a library developer, you have to be a good citizen and avoid changing the methods that your library contains in incompatible ways. You have, when you do perform incompatible changes, you have to communicate those changes to the downstream ecosystem by using server properly, etc. So this creates a kind of burden for library developers that is really, really hard to deal with, especially when you're working on libraries on your free time and you're not paid for it. Like there's a balance between what you promise to your users versus the changes that you'd like to make to your library to improve ergonomics or whatever. On the side of the application, so when you are working on a product for your company and you encounter a binary incompatibility problem, solving it can be really hard because you have to know the metagame of the ecosystem, right? You have to know which libraries depend on which other libraries and understand how to find the right combination of versions that will eliminate the binary compatibility problem. Can sometimes use shading, but it's really hard to reason about. Or you could potentially decide to fork literally all your dependencies and maintain their release cycles. But that's prohibitively hard, right? Nobody's going to ever do that, or it'd be crazy. So this is sort of the axis or thought that I'm going to use to present the Unison programming language. I promise I'm not going to show too much code. It's more to induce a kind of mental model for what Unison does differently than traditional programming language that I'm giving this talk. So Unison is a purely functional programming language that looks a little bit like Haskell in terms of syntax, with the difference that it uses abilities as a way to compartmentalize side effects as opposed to monads. And it's also using direct style as opposed to like monadic big combinators. It was initially built by, and still being built by, two of the three authors of the Scala Red Book. So Paul Chusano and Runar Bjarnason. So it's actually quite relevant to our community, really. So the difference between, or the sort of thing that's very unique to the Unison programming language is that rather than identifying the terms by human given names, the terms are identified by the hash of their contents. And code is stored not in files, but in a database. So what does this mean in practice? So essentially, when you write functions like these in Unison, so these are very simple increment function that adds 1 to a number, to a natural number, and then one that applies this increment to all elements of a list. What the compiler is going to do when you're compiling the Unison code is that it's going to sort of normalize the definition by changing all the terms you're referencing in your definition with their hash. So you can see that in this first function, for instance, we're referencing a sort of primitive function, so the hash is sort of hard-coded to this hash nats.plus thing. But then in this other function, we can see some other hashes which represent the list.map function, and then our previously defined increment function here, and then the argument. And once the compiler has done this for the function definition, it hashes the right-hand side of the function, which creates the identifier for that function. And then it stores these in a database. So the left-hand side, it's a local database, typically on your computer. So the identifiers will be the left-hand side, and the right-hand side will be the value of the functions. Names are stored separately in another table. So there are essentially like aliases to functions instead, or aliases to terms instead of defining identifiers. So yeah, that's the sort of idea, the central idea around Unison. So now it's all nice and well, but like, how do you even code? How do you even, use a database to store your code, etc.? So I'm going to point you to the UCM tool, which is essentially a bundle of tools that embeds a compiler. Like, it's a REPL, essentially. It embeds a compiler / a build tool. It embeds a code browser, so you have a command line. You have commands essentially to find terms. You can sort of browse through your code base. You can open the code base in a web page if you'd like. You have Hugo, which is like Google is a Haskell tool, but essentially it's a tool that lets you search by type. So, for instance, you can search your code base to say, give me, or is there a function that turns JSON into a string, this type of thing. And it contains also a version control thingy. And Unison implements the language server protocol, and it also provides a VS Code extension. So stand back. I'm going to attempt doing some live coding in front of your eyes, if I can. Cool. Can everyone see this? All right. So I've got essentially I've got the VS Code extension installed, and all of my code is going to be in the Scratch file. All right. So this terminal is the UCM tool is open in this terminal. So what I'm going to start doing is creating a new project. So it's loading the standard library in there, and I'm going to start writing some code. Actually, I can do something like ls to show what's already in there. So for instance, I can search for the terms that are part of the standard library, things like float, things like IO, local time, etc., either, this kind of stuff. So I'm going to implement the increment function, doing like this very simple thing in my file. And when I save the file, I get this message from the compiler saying, oh yeah, okay, I've recognized that this function is actually well formed, and you can add it to the code base. So I'm pressing add now. The squiggly lines are only there at the very first function you have in your code base. But once I've added the function in my code base, essentially I can remove it from the Scratch file, and it will now be in my little database there. You can see the inc function here. If I want to make changes to it, I can do edit inc. Oops. And obviously it's the demo effect, so it's not actually going to work. Okay, I'm going to add something else, let's say. So the inc all. Of course, that was bound to happen, wasn't it? Integral list.map, inc list. I've got a compiler error because that's supposed to return a list. I'm going to add inc all. I'm going to remove this. I can view the definition here in my terminal, and in theory, there you go. So I can load the definition back into the Scratch file to make changes to it, right? So if we want to write a hello world, for instance, it would look like this. Without diving too deep into what it means, I'm going to do like get the args of the main program. I'm going to match onto the head of the args and do something like some value print line hello plus value non print line hello. Cool. Main, and then I can run main, like run main John, hello John, run main without arguments, hello. Cool. So that's about it. This was a very, very short showcase of what it looks like to code in Unison. All right. So this is all fancy and fun, but how does it solve compatibility problems? So I'm going to assume that I'm sort of starting again from I'm deleting everything from my local database. And in a Scratch file, I'm going to define these three things, which look very similar. As a matter of fact, the two first functions are exactly the same, but they are in different namespaces, right? That's how you do packages in Unison, if you'd like. The last function differs in definition, and it's this sort of v2 thing, .2, whereas the first two ones were 1.1, libv1, libv2, etc. So I've got like I've defined three functions, but when I add them to my database and when I call the names, passing the sort of inc name to find all the things that contain the inc name in it, I can see two entries in the table, meaning that the compiler was able to reconcile the fact that these two first functions are actually exactly the same, and they just have different aliases, right? And the third function, which has a different definition, is actually stored differently in the database. So now, as a little question for you guys, let's say I do this. So I rewrite my incremental function, calling map, and I'm not fully qualifying the function that I'm trying to map over my list. What happens? Do I get a compiler error? Show of hands. Yes, I actually do. Okay, because I had 3 functions, right? And 2 of them were containing the inc segment. Or I had 2 different, like physically different functions that were containing the inc segment, all right? So the compiler is saying, okay, I know that you've got functions in your database that match this definition, but I can't really know which one you mean. And it's telling me like how to disambiguate. So now I'm doing the same thing, but I am adding only 1 additional segment to my function definition here. So I'm still not fully qualifying the function, but just by virtue of the fact that the 2 1.inc functions were physically the same, the compiler is able to say, okay, well, there are different aliases, but those sub-aliases are actually matching the same thing, so I can disambiguate for you. You don't have to be more precise than that, right? So it is completely fine with adding this thing. So disambiguation is only required when names point to different hashes. Now let's talk about libraries. So Unison being database driven means that Git and GitHub do not really cut it. So it comes with its own code storage solutions, which is Unison Share, and it's a very nice tool, and in the sense that it benefits from the model of Unison that is stored in database with unique hash for functions. And it means that all the code that you see in this web application is actually hyperlinked. So you can literally hover onto any term, and it will give you the signature of the term, and you can click on it, and it will open the definition for that function. And because things are uniquely identified by their hashes, no matter where the definition comes from, whether it's from a transitive library or whatever, it will be able to sort of load the definition and show it to you. So that's actually super cool. And when you open this web app as well, you sort of point it to a library, you get this little button here that you can click on to get this little helper to say, well, if you want to install this library in your code base, here's the command you run. So something like libinstall at Unison, which is the organization of the library / the name of the library. Right, so we're gonna assume that we're installing a JSON library into our code base. So you can see that's typically the kind of output that you'd get from the terminal, meaning that rather than downloading a jar that contains a bunch of things, it downloads actually the entities, the granular entities, the granular terms. So you have this sort of notion that the library is actually just a set of granular terms that can be referenced independently from the library itself. And what it does when you install a library, in addition to loading all the terms, it actually realiases the names of the terms by prepending the coordinates to the library, so that you have the name of the organization, the name of the library, and the version of the library. So that if you have an ambiguity between 2 versions of the same term, you can actually say, okay, well, I mean this particular version of that term. All right. So yeah, that's the sort of pattern for the prefix that the build tool adds to the terms of loaded libraries. So imagine that you install another version of the core library for whatever reason, or maybe it's loaded transitively by installing something that depending on it. Then when you call the names command with the JSON name, it will show you that both versions of the terms are actually pointing to the same physical definition, right? So when I have two versions of the library in my class path, so to say, the things that are actually the same will be physically the same in my code. So the libraries are very granular, and that solves both source compatibility in the sense that you can reference the different versions of a single name, but also it solves binary compatibility because you have this granularity and you don't have to treat the libraries as bundles that may contain incompatible versions of the same thing. All right, so that's all neat. It's actually, I personally find very interesting in terms of the score ID, etc. But when you sort of weigh that with the maturity of a language like Scala and with the ecosystem, etc., does it bring something that's actually that valuable to the table, right? Is it really that valuable? So in itself, probably not. But there's an additional benefits to this model. Like I said, there's global hyperlinks when you have your navigating the code. You don't need to search by strings. You can literally click on a term and get the definition from that term loaded directly in the page. It's really nice. You have the ability to search globally in Unison Share, which is really nice as well. The compilation is basically instant because of this granularity. You never have to recompile a code base. As soon as it's being compiled on one machine and uploaded to Unison, essentially the model is going to be accompanied with this trust kind of thing that will just require the verification of the hashes as opposed to the type checking. So essentially, it takes a little longer to load the library, but you never have to recompile anything. It's great. Instant renames because the names are stored in a separate table than the definition, so it's working very, very well. But really, the sort of killing feature is this particular thing. It's the value type that's a built-in type in the Unison standard library. And what it does, or what the sort of API around it does, is it lets you serialize any term. And by any term, I'm talking either data or behavior. So I can literally serialize functions. And I can get the dependencies of these terms, right? I can, in the runtime, get a list of all the terms that a function depends on. So what this means is that we can build protocol for distributed computing. So essentially, it works a little bit like this. So you're imagining that you have one computer that runs Unison that wants to ask another computer to run some function. And so there's going to be this protocol when it's going to be like, hey, can you run this for me? So you're going to send that serialized form of a function to another node, and the other node is going to say, oh, yeah, I could, but I'm missing these terms. Can you send them to me? And then the first node will say, okay, sure. Here's the list of everything that you're missing to run the function that I'm asking you to run. And because everything is sort of uniquely identified by the hash, there's never a contextual problem of having different class paths, etc. It's really easy to think about code in a distributed context because of this particular model. So everything that I've shown so far or talked about so far about Unison is open source. The Unison compiler is open source, or Unison language is open source, the tooling is the VS Code extension, the Unison share is open source. The thing that's not open source is the Unison cloud product that Unison Computing, the company that builds Unison, has built on top of this value construct. Essentially, it's a cloud solution that's a paid solution. The prices are honestly quite decent for what it brings to the table. There's a free tier, so you can sort of play with it, see what it feels like, etc. And it's written completely in Unison. It's completely dog-fooded. They've not cheated by running some Rust program in the solution. They've actually built their cloud solution directly in Unison. And it lets you essentially reason about distributed systems with this high-level, very simple language. And so to give you like a very, very small taste at what it can do, because it can do so much more, but basically this is a 10 lines program that both define an HTTP service that just returns hello world, but also deploys it. So essentially this is the application logic here. It takes an HTTP request, it returns an HTTP response, nothing too fancy about it. And that's going to run on the cloud. You know, like it's a term that I'm defining on my computer. It's a function, but it's going to be running on the cloud because I'm going to be sending this function to the cloud and asking the cloud to run it for me. So this runs on the cloud, this runs on my local machine. I'm saying cloud main do deploy HTTP blah, blah, blah. Here's the function that I want to deploy, and that will send the function to the cloud. The cloud will ask me whether there's anything that is missing for running this function, and without me having to do anything. And in order to run this application on the cloud, it's a one-liner method, run this main method. And once you run this, essentially you get this message saying, well, this service was exposed successfully. Like it's 10 lines of code that do both the domain logic and the deployment. There's no packaging, there's no Dockerization, it's literally just that. So that's quite fantastic. But on top of that, there's all sorts of like very interesting construct for dealing with distributed problems, like distributed promises, the ability to sort of ask for a remote location and send it code. So basically, you could re-implement a very naive version of Spark a very simple version of Spark, should I say, in like 100 lines of code of Unison code. There's things that have vocation to essentially provide you with the same capabilities as Kafka or Kinesis, but written as libraries instead of products, and with the kind of combinators that you'd expect from a collection library like filter, map, etc. This kind of thing. It's really, really interesting. So as a conclusion, I'm going to leave you guys with this particular statement, namely, or my personal interpretation is that Unison is to distributed system what CatEffect.io or Aux are to concurrency. So yeah, that's it.